Thank you. Thank you very much. And as a matter of fact, the topic of my talk is the use of artificial neural network. We have been doing quite some work in different fields of concrete technology and structural engineering. So I put here the title, Mulit-Fold Performance of Advanced Cementitious Composites. And, well, rather than come with a certainty, I come with a question. Can we transform information into knowledge? Because that could be the purpose we are going to use artificial intelligence now. So you can likely recognize this building. This is the oldest concrete building in the world. It stands there for about 2,000 years. And it's still the largest unreinforced concrete dome, about a little bit more than 40 meters in diameter. And when I arrived in, when I checked in at the hotel and found a way to my room, which was not easy, I have to say, coming here, I ended up in this other dome. This is about 1900 years later than that, still is the largest fixed dome structure in the world. But the principle of the structural mechanics are exactly the same. The Romans probably had a hint of how a dome did work at the mainly compressed structure. They removed here this part, so having the knowledge of the circumferential behavior of the dome. But the principles are exactly the same. But if we look at buildings, at future buildings, these are two buildings which share the same name. They are both called the Museum of the Future. This is in Rio de Janeiro in Brazil. This is in Dubai. It's completely different. And actually, when I wanted to see them, this sentence of Winston Churchill came to my mind. We shape our buildings, and thereafter our buildings shape us. So this is something which led me to think, so how do we imagine our future? And as a matter of fact, if you look at the ACI committee directory, you can see that there are some advanced technology or some consolidated technology. So we have fiber-reinforced concrete, ACI 544, dating back for more than 60 years, self-compacting concrete, a little bit younger, recycled aggregate concrete, 3D concrete printing, quite new brand committee formed a few years ago, and lunar concrete, ACI 565, which exists for about 2 years now. So I decided to look into Scopus and see, okay, which is the trend of publication, which is the trend of new information coming about these technologies. So this is fiber-reinforced concrete. If you Google these 3 keywords, you see the trend. The first papers appeared in the early 60s, but then the trend is this. And the number of new papers that we publish increased every year by 200. So last year we had more than 4,000 papers published on this technology. This is something that a human being cannot cope with, simply. Well, self-compacting concrete, the trend is a little bit more encouraging, but still we had about 800 papers published last year on this topic. Recycled aggregate concrete, we go back to 1,000 papers, more than 1,000 papers per year. 3D concrete printing, 600 papers per year. There are a lot of PhD students now working on this topic, which means that they should read 2 papers per day, even working on Saturday. We are a little bit more lucky on self-filling concrete, but still there are 400 papers per day. And if you look into lunar concrete, you have this strange trend for which, being an engineer, I calculated the derivative. For this curve, you cannot calculate the derivative. But what does this mean? This means that we have about consolidated technologies or innovative technologies, a number of papers published per year. You can imagine there has been somebody doing research, writing, there have been reviewers going back and forth, associate editors. So this means a lot of work for the community. But there is a lot of information which is spread out. So the issue is, how can we transform this information into knowledge? Can artificial intelligence help us? Well, I am a little bit man of a certain age, but I remember when I was a student, we still had the paper journals. We had to subscribe. And there was a service in the department for which you registered for the journals. You have them for 2 days, and you look at that, made copies, and then read the papers. Nowadays, we can have this information with a click immediately. So I have I recommend the reading of this book. Is The Age of Artificial Intelligence. One of the authors is Henry Kissinger, and there are other two academics. I've read it, I found very interesting. And there is this sentence which hit me. The internet inundates users with opinions of thousands, even millions of other users. But we do no longer have the time for sustained reflection, which is what transforms the information into knowledge. We do not have the space and the time required for deep, concentrated thought. So, is artificial intelligence going to replace this space and time which is now lacking? As a matter of fact, there is another interesting thing that I've learned reading this book. We are used to think of computers, at least when we learned programming, computers did exact operations. You program the computing machine to do a series of operations which are very well defined. And as a matter of fact, the research in artificial intelligence started in the same way, and it failed. Only in the early 90s, some, renegade researchers, they wrote, they realized that artificial intelligence, in order to exist, had to be imperfect. Because they started with image recognition, the image of a cat, and was a failure. Because the cat, it has not a definite position. You can have it infinite different positions. So then they realized that in order to recognize a cat, the artificial intelligence must be trained, learning by errors, which is exactly what we humans do. So in this framework, we have started applying artificial intelligence just to try to derive from this huge amount of information the knowledge. And we ended in another challenge. So the first topic we dealt with my research group was recycled aggregate concrete. I will tell in the end which was the purpose for this. So we started interrogating the databases, typically Scopus, and we have to decide what are we asking for. So we ended up with this data on the recycled aggregates. We wanted the source, we wanted the location, the original element, and probably, most likely, the strength of the parent concrete. This was a useful information. Then, obviously, we wanted information about the geometry, the density, and all the possibilities on the mixed design of the recycled aggregate concrete. And if you set up this data ontology very precise, you end up probably in greatly diminishing the amount of useful information that you find on internet. For example, the parent concrete information in most of the cases is missing. Well, this is not a criticism against, because we do the work, sometimes we do not know, we cannot publish. But I definitely think that if we want to foster this kind of technologies to be standardized, to be widely accepted and so on, recycled concrete aggregates one thing, but all the other ones, we need to agree on a data ontology. When we publish, we must have a minimum set of information that must be in the paper. Otherwise, we are making good research, I do not criticize, but that paper will not contribute to the increase of the knowledge because we remain confined in itself. Popper used to say, Karl Popper, a philosopher, that an information to be scientific must be falsifiable. You must have all the tools in your hand to demonstrate that that information is not true. Then probably you will end up in recognizing that it's true. But you must be able to demonstrate that it's not true. So in the end, you see, we ended up with selecting 100 papers with 1,600 more information. Many of them came from China, but there was also a good geographical distribution. And we looked into compressive strength, the easiest thing that everybody will do. We trained our neural network, but we ended up with a very large error. 25 megapascal plus and minus, totally unacceptable. So in the end, that is what, extract patterns from large data sets, but then there was time for a sustained reflection. The student came to me and said, well, I have these results. Then you have to sit down and look into that. Sustained reflection. And I asked her, look at the frequency of your data in mixed designs. So we realized that there were very few papers which had slag or other supplementary cementitious material different from fly ash or had fibers. This very low frequency paper actually jeopardized the database. So simply said, let's try to remove them, and the error was greatly reduced because you see we went from 25 to 14, a little bit less. Then, okay, you can rely upon the removal of the outliers, and we ended down with an error which we deemed acceptable, which was below 7 megapascal. But why did we deem acceptable that? That brings us back to the human tool. Because, for example, when you look at the structural design codes, there is the rule of thumb that go from the average strength to the characteristic, you can subtract 8 megapascal. So that is some variability that we do accept in our current concrete technology production. So we deemed this prediction acceptable. And then we said, okay, let's include the parental strength information. Immediately, the error increased because this was an information that was not present in all the papers. But this is an important information if we want to spread this technology, if we want to set up a reliable value chain for recycled aggregates to be used in concrete and so on. Well, after having said this, we wanted to validate our tool. And we went back to the original project, which led us to the idea of setting up this database. Actually, we had this project funded by the European Commission to set up a circular economy protocol or ideas for coal mine waste geomaterials. It's a huge problem, especially if we are going to dismiss the coal extraction for the production of electrical energy. So what we did, we used both coal mine waste geomaterial as recycled aggregates. You see, you can distinguish, you can recognize this from the parental strength because these materials are very weak in compressive strength. But then we also crushed back the concrete containing these materials and used this the concrete already containing recycled aggregates, we used it back as a re-recycled aggregate in a sense. So this concrete here contains recycled aggregates coming from a concrete which already contains recycled aggregates. And you can recognize from the parental strength. We were quite happy because the prediction of the strength that we got matched quite well the results of the experiments that we did. Actually, these materials here were already in the neural network, these were new. Then we moved to another topic on which students have to read several papers per day to cope with the publication, 3D printing. You know, we have these properties or these keywords, pumpability, extrudability, buildability, which are key for the successful application of 3D printed concrete. But hardly you have something quantifiable then. How do you quantify pumpability? It's a yes or no. I tried my mix, I pumped it, and it worked well. I tried my mix, I pumped it, and it clogged in the pump. That is what you have. Extrudability, I can extrude it in a continuous filament or I cannot. Well, as a matter of fact, there are ways to correlate these, requirements for 3D printability to fundamental properties of the material. The pumpability you can correlate to the Bingham yield strength. The extrudability you can correlate to the early age tensile strength because you are extruding a filament. So if the filament tears off, it means that you have exceeded its tensile strength. And buildability you correlate to early age compressive strength or Young modulus as well. So also in this case, we had to decide which were the keywords we used to interrogate our database to extract the data. Okay, 3D and concrete and printing is the starting point. But then we wanted information on the mix design, which for 3D printing mixes is like an Arabia Phoenix. You don't find it in most of the cases because they are protected, patented, and so on. But we also wanted information on the rheological properties. So we asked yield stress or viscosity, and we ended up with 254 records. If you ask yield stress and viscosity, which means that the study measured both properties, the number of records is greatly reduced. It's true that viscosity is not so important in the sense of the printability. The yield stress governs more, but you can ask it as well. So we started building up our neural network. So we started with 10 input neurons dealing with the data on the mix design, and we tried with 2 output neurons, the yield stress and the viscosity. Very poor prediction because we had very low data. So then we simply said, okay, let's try to split the 2 neural networks, having 2 separate them with the same input but working on each different output. So one on yield stress and the other one on the plastic viscosity. And it worked well, and what we ended up with were what an engineer does want is a design card, because in the end, probably he has to say, okay, I have a mix. I want to see whether it's printable, and if it's not printable, I want to have some tools which guide me to adjust the composition in order to achieve my requirements, to achieve the printability. So we ended up, this is published in the proceedings of the RILEM Spring Week 2023, with design cards like this, which correlate the yield stress, the static yield strength, to different mix design variables, which could be the cement content, the binder content, and the super plasticizer content. Actually, this was possible thanks to the use of neural network and artificial intelligence, which helped us to process and to have some reliability confidence on this data. Obviously, we wanted to check the reliability. So my student, Francesco, was standing there with the oranges, whether he picked up randomly, said, I want to print some mixes. So we ended up with a paste, we ended up with a mortar, we ended up with a mix containing geopolymers. So we designed these mixes with the aid of the neural network. We had information from the neural network on the rheological properties, the yield stress, which was this. The neural network predicted these values on the second line. We casted the mix, we printed it, we measured the property with a rheometer, and we ended up with predictions which had an error maximum of about 7%, which is, by the way, acceptable, considering also the large variability of the information that you have. Other application, self-filling concrete, quite a new technology. So we interrogated our database for the dosage of cement, mix design variables, and we had this information on the crack width, age of healing, and the self-healing environment. Our output in this case were different parameters to quantify the effectiveness of the healing, so recovery in crack size closure, in permeability, in ultrasonic pull velocity, and so on. And also in this case, we ended up with design cards. In this case, our goal was, which is the maximum crack size that in a given condition I can heal? Because that is what an engineer will ask you. I tell you, okay, my concrete heals, and they say, okay, but which is the crack width that I can heal? So that is the information which we wanted to extract. And in the end, we also realized that since it's difficult to find a consistent database, we worked on this project, other European project, for 4 years. So we ended up with information about more than 700 cracks. We monitored all those cracks for up to 1 year. So we have about 3,000 of images that constitute our database. We interpreted them with statistics, trying to calibrate a crack closure kinetic response. Then we used artificial intelligence, and in the end, we realized that if you use AI, what you get is a prediction which is much narrower than what you can get with statistics, because of statistics, you just end up with the best R-square. So summing up, conclusions. Well, I will not say conclusions. Citing once more Kissinger, rather than clear outcomes, we more likely will use artificial intelligence and end up with a series of imperfect answers, but at least are some answers. So this is the positive way to do that. So the thing is, anyway, this. Shall we continue to use AI only to manage large quantities of data simply because our human capacity exceeds that, so it helps us? Or probably, shall we push the boundaries forward and explore, for example, domains which so far we have taught as deterministically? To measure the properties of a material, we make a test. And we interpret the results of a test through principles of continuum mechanics. Shall probably we reshuffle that and use artificial intelligence also to go beyond that? The other thing is that created by humans, AI should be overseen by humans. The example is exactly these trials that we did. We realized that if we want to consistently use AI in having tools which help us in concrete technology, for example, we must agree on a data ontology. We must agree on a minimum number of information that we must have in each of our published research in order to make that research useful to extract information from those papers and transform that information into knowledge. Well, all this work has obviously been done by my fantastic research team. There has been a lot of PhD students, some of them now graduated happily in the end, and also master students who proceeded with PhD in some cases. And I also thank the funding agencies and projects which have helped us to perform this research, and thank you for your attention.
All right, we have time for 2 questions.
Thank you, Professor, for your excellent presentation.
Thank you.
So in one slide, you showed that you removed outliers from the strength results, and the accuracy was, like the variation was decreased from 25 to 14%.
From 15 to, yeah.
So, like in my experience, even if I have like 1,000 data, if 50 of them are outliers, the error is much, much larger than 5%.
Yeah. That is probably an ontological issue. It's something we have to work on because it's really the problem when you have these large sets of data and the criterion that you have to use to remove the outliers. Sure. There are also, AI techniques, tools that can be applied to remove that. We have started looking into them, and they have also, fascinating ways of working because they are based, for example, on the way in which the wolves hunt the prey or the way in which the whales recognize them. So it's really a fascinating environment. But I think that really that one is the topic in which we have to work on, but we have not to forget that we are engineers. Sure. So those tools are fascinating and perfect from a mathematical point of view, but then in the end, you must use your judgment. There are sometimes probably cases in which you recognize an outlier without the need for artificial intelligence. The issue is that if you have thousands of data, you will get tired of recognizing the outliers in the end.
Thank you very much. Yeah. The other question is, how did you extract those data? Was it like done automatically, or was it like a student?
Was quite a painful work for the students, I have to say, because extracting data automatically, you introduce another source of error, I would say. No, it was really, I think that in that case, that is the human overseeing of the artificial intelligence. At least into that, you must agree on the ontology at the beginning, and you must have some carefully supervised work to extract the data. Yeah.
All right, let's thank Professor Ferrara again for his great presentation. Thank you.
Thank you very much.